Today I'd like to talk to you about our Hirose RF connectors, and I'll focus on a couple of series in particular, but in general the RF connector series. The first slide, excuse me, I seem to be locked up here. This happened to me once before. There we go. So the first couple of slides I want to show you are just an overview to give you an idea of the breadth of products that Hirose offers in the RF connector world. So here you can see a listing of standard RF connectors. By standard, I mean these are industry standards that a variety of competitors offer. Things like SMA connectors and BNC connectors. So Hirose manufactures all of these, and we've got some challenges from time to time in the marketplace with pricing, but Japan is working hard to get us more price competitive on these so we can grab a little larger market share. The next slide is, again, a large variety of custom design RF connectors. That is an RF connector that doesn't fit into one of the standards like an SMA or a BNC, but it was typically driven by a customer demand or a customer requirement, and we're now producing these products and selling them to the general market. So some of these I'm sure you're familiar with. In fact, we're going to touch on just a couple of series that by surveying salespeople I know that you're aware of, but I just want to touch on highlight on a couple of them. Before we get into the connector offering, I want to just touch on a couple of technical points because we'll be talking about these as we go through the connectors themselves. There's really three terms I want to talk about. One is, the first one is impedance. So that is the transmission characteristics, typically expressed in ohms. For all of you who were in the Greek system in college, it's represented by the ohm signal there, you can see. So most standard communications are in 50 ohms, broadband are in 75 ohms. There are other standards as well, but one of the performance characteristics of the connector is going to be determined by how close to 50 ohms or 75 ohms you can get. So the idea is to match that number, and that's done by simply dimensional tolerancing and how good of a connector you're building in that terms. There are other things like the material for the insulator that affect that number as well. But again, it's how close to 50 ohms can you get. The second term is VSWR. If you're talking with some engineers, they might refer to that as VSWR. So if you hear VSWR, sounds like a French term. It's really they're referring to the voltage standing wave ratio. And this, if you're following my mouse here, on this illustration, you can see you've got a large signal coming into the connector, and then depending on the connector's performance, you've got some degree of back reflection represented by this smaller arrow coming back. So essentially, it's a term that is used to measure how effective that wave ratio is. The closer to 1, the better the performance. Typical value of a connector is 1.3, just to give you some feel for what that range is. But the closer you can get to 1, the better you are. And the third term I want to talk about is insertion loss. So this is how much does the signal degrade as it moves through the connection or through the connector. Expressed in terms of impedance, or the units are negative dB. So here, again, in this illustration, you've got a large arrow representing the large signal coming into a connector, and then there's a smaller arrow coming out of the connector. So that's measuring your insertion loss. It's determined by the impedance that we talked about before. So how close to 50 ohms can you get? The farther away you are from that target value, the bigger your insertion loss will be. the conductive resistance, the resistance of the connector itself, and the dielectric loss moving through that connector. And the insertion loss, typically the smaller the value, the better. So let's get into a couple of connectors. The next two connectors that I'm going to talk about are the ones that I've been told that you as our sales organization are pretty familiar with. You've been selling these for a while, but I just want to highlight them again because they're big market potentials, and Hirose does a great job at these, designing them, building them at a cost-effective basis. So the first one I want to touch on is the FL series. This would be a very small connector. You can see down here in the bottom there's a UFL, WFL, and an XFL, and we'll get to the sizes in those just a minute. But the application is all the same. So essentially it's going to be used inside of a device. So you've got a antenna board here, and you need to make that connection to a RF board. So you've got a connector on each board and then a small cable assembly that takes that signal from one board to the other. Something worth noting here is not only the connectors, but Hirose is supplying the RF cable assemblies as well. Typically, Hirose, as you know, doesn't build cable assemblies, but in this particular arena we do. Here's another application for that same type of connector. So in this application, we're going from that board to an external connector, or to an external antenna, I'm sorry. So here you can see we've got our FL connector mounted onto a printed circuit board with a cable assembly that goes from that FL to another FL, connects up to a larger machined connector like an SMA or BNC, and then it goes out to an external antenna. Here are a couple of examples of, here's an SMA connector connected to a UFL coax on a board, and here's a TNC connector, double-ended, going to a board on a UFL. So that's a pretty typical application. From a size standpoint, there are a variety of FL connectors that have been developed over the years. You can see here in 1995, we started out with a 3mm size. We're currently down to an XFL, which is under 1mm in size. Just worth noting, the XFL is also available in a board-to-board version, where these others are a cable-to-board only. The next series I want to touch on, again, this is one that you should be aware of or you've been selling for a while, but again, it's worth highlighting, is our MS series. And actually, it's a little more than just a connector. It's we refer to it as a active RF device because it does a little more than just connect. It connects, and it also has a switch inside. So in this application here in the bottom left, we've got a internal antenna on a board like you would have on your cell phone. And then you can connect an external antenna to it, and it actually switches from the internal to an external antenna. If you look in the upper right here, we'll have a little demonstration of how this works. So you've got a signal that comes in, comes up into the connector, goes through the connector, and goes to an internal antenna. So in this case, when a cable is not plugged into it, we've got that signal goes through the connector into an internal antenna. In the bottom right, we're actually going to connect that cable assembly or the external antenna to the connector. So we've got our signal comes in, it stops at that point, goes up through the connector and out through the cable assembly. So now we're connected to an external antenna instead of an internal one. And just like the FL series, they come in a variety of sizes. Over time, we've gotten smaller and smaller. Of course, as you get smaller, you lose some things like durability. You can see in the first couple here, we've got durability of 12,000 cycles down to the smallest MS series. We're down now to 100 cycles. So it's going to depend on your application, size requirements of that application, and durability requirements. Now I want to touch on 3 connectors that are all going to have very similar characteristics. The first is our HRM series, the next will be the HK series, and then the third is the H2.4 series. They're going to be similar designs, similar applications, but there are some differences between them. So let's get going on those. So the HRM series, first off, that's equivalent to a standard SMA connector, if you know that term. The HRM is the Hirose term on it. Comes in 2 versions, which is the first is a vertical type, and the other is a right angle, or it's sometimes referred to as an end launch version. Supports high frequencies up to 28 gigahertz, available in the vertical or right angle. Instead of soldering onto the board, you actually screw this connector onto the board so it can be reused. There are a number of advantages that we'll talk about in just a second, but it does not solder to the board, it screws to the board. And of course, it's RoHS compliant. The 3 connectors I touched on, the HRM, the HK, and the H2.4, Hirose is in the process of doing a promotion on them. They're all in stock at DigiKey, and in fact, DigiKey has added them to their website. So you're going to be seeing more of these connectors in the marketplace or promoted by Hirose. Some dimensions of the HRM. Again, this is a standard SMA type, both in vertical and right angle versions. Performance. So we're talked about before about insertion loss. So you can see on the end launch here, we've got a negative 2 dB, which is pretty good. On the vertical type, which is typically going to have a better performance, you've got about a negative 1 dB. And the Viswar, I don't know what color this is, maybe pink line, is an industry standard, and you can see that we're well within that standard for the end launch and for the vertical type. So again, let's go through some details. So instead of soldering onto the board like the one on the left-hand most picture is, when you solder it onto the board, you get a conductor that goes through the board, and you get something called a stub on it. So there's a stub which creates a signal back reflection, which degrades the performance. So you actually get a much better performance with the screw mount here on the right. You get no stub with the butt contact. That's simply a pressure contact between the board and the connector. And again, instead of solder down, you have 2 screws that hold the connector onto the board. Reduces back reflection. On the end launch type, again, it screws onto the board. It has a center conductor here that interfaces with the board. On this one, you can solder it. Soldering is recommended to get best performance, but doesn't have to be. But the outer shell is fixed with screws. So the products requiring soldering onto the board, you're going to have less ability to reuse them a second time. There is certainly a better chance for floating on the board, as that hole, that center conductor hole, is not exact. So you've got some floats, you're going to have some mismatch, and you're going to have a poor performance. So you've got an excellent high frequency performance, and you can actually reuse the connector. The other large advantage is you can use it with a variety of printed circuit board thicknesses. Since there's no center conductor, you have to be concerned about the length of the contact. You can use it with a thin, medium, or a thick board. We're recommending a 0.7 millimeter minimum only to prevent bowing of the board, but really can use a variety of PCB thicknesses. So it's a quick, stable connection between the connector and the board. Eliminates soldering skill, so anyone can really mount this and get a good performing connector. The screw mount provides easy, seamless, quick assembly. Some typical applications you're going to see in a measurement device. So you've got a couple of PCBs with a whole variety of connectors mounted onto it. These can all be screwed onto the board by an intern. Provides temporary high-frequency measurement, and then when you're done measuring this board, you can take all the connectors off and reuse them on another board. Other applications, typically where you would, and actually any application where you would typically see a RF connector, this type of connector can be used as well. I want to touch on the HK series now, which is a very similar design, has many of the advantages that you just saw in the HRM series. Only this connector now operates at 40 gigahertz. If you remember back to the HRM series, it ran at 28 gigahertz instead of the 40. The 2.92 refers to the inside diameter of this connector here, this is an industry standard, conforms to a mill standard. 40 gigahertz, higher frequency, more expensive connector. So that would be a typical question I would expect would be, well, why would I use this connector? Why would I use the HRM if I can use the HK and it's a better connector, I get higher frequency? Well, it's going to be a more expensive connector for starters. That's probably the biggest reason. And secondly, it depends on what your equipment is, if you need the HK as an industry standard. Again, screw mounting, just like the HRM, accepts flexible printed circuit board thicknesses and a stable ground plane with a gold-plated grounding surface. Some dimensions. Actually, on the illustration on the left, you can see the interference fit that's designed into the connector, so when it mates with the printed circuit board, that's the amount of interference you get. And you've got a gold-plated ground plane on the bottom, which you would typically have a stainless steel on a through-hole version. Here are a couple of charts showing the Hirose performance against a competitor. There's one large competitor on this product line, represented by this red line, represented by the color of their logo. And you can see the blue line represents the Hirose performance. Very good performance, very stable, just over 1.1 Biswar, where the red line here is way off the chart as you're getting out towards the past the 30 gigahertz requirement. Insertion loss, again, we're at just over negative 0.2 dB, where the red line is again going way off the charts once you get past 30 gigahertz. So from a sales standpoint, that's something you can really use as a sales feature. Some specifications, again, it's a 50 ohm connector, 500 cycles. Worth noting, you can see down at the bottom here in the grayed out section is the Biswar or the BSWR performance. Again, you can see that the performance is measured based on what gigahertz range you're in. So if you're at 18 gigahertz, you're at 1.1, at 26.8 gigahertz, 1.15, and at 40 gigahertz, it's at 1.3. So when you're talking with the engineer, what are their requirements, it's good to know what gigahertz range that they plan to work in. Again, applications like we saw before. This is just the same slide. And then the last connector I want to touch on is the H2.4 series. So this is, again, a similar application, similar type of connector, but this one now is operating at 50 gigahertz. If you recall back, the HK was at 40 gigahertz, and the HRM was at 28 gigahertz. Again, you're going to pay more because it's a higher performing connector. The 2.4 is referring to this inside diameter, and the gigahertz range, in other words, moving from 40 to 50, is going to be dependent on the distance from the center conductor to the outer, or to the inside diameter here. So as that distance gets smaller, you get a higher performing connector. And along with that, the tolerances get tighter and it gets more difficult to make. So the H2.4 you'll hear as a standard connector, so if somebody's looking for an H2.4, that's what they need. Operates at 50 gigahertz, screw mounting, just like the previous two you heard, accepts flexible printed circuit boards and stable grounding with a gold-plated surface. As you can see, the general trend in the market is higher frequencies, higher transmission speeds. So we're going from an SMA to the HK to the H2.4. Like you saw before in the HK series, this is the center conductor and how it interferes with the, or designed in interference with the printed circuit board to get your electrical signal. Again, gold plated. And here are some competitive charts showing the Hirose performance in VISWAR as well as insertion loss. So we've got a closer to zero insertion loss than our competitors, particularly at the 30 gigahertz plus, and the same issue with the VISWAR. As your frequency is increasing, the VISWAR is going up, but the Hirose is a very stable connector. Same sort of story on the plug. This slide you've seen before, but let's just touch on it again. So we've got, with the screw mount, instead of the solder mount, we've got no stubbing and minimizes back reflection. Again, printed circuit board thicknesses. So with one connector, you can use a variety of thicknesses of boards because you don't have to worry about matching the center conductor length with the printed circuit board thickness. Touched on this before, but you've got some of our competitors are using a simple, the shell ring. It's a one-piece design. The Hirose connector is a two-piece design, so you've got a gold ground ring on it, so you've got better performance, again, with the gold-plated, which would be the same material as you would find on the pad on the circuit board. And we offer it with or without the hardware, so you can buy it either way. If you went on the DigiKey website, you would find both options available for you. And the application, as we talked about before, same application, same slide, actually. Again, the specification sheet, so we're looking at a 50-ohm connector. Durability can be mated 500 times. And again, the VSWR is expressed in terms of different frequency ranges. So you've got 26.5, 40, and 50. You can see that you've got different performance at those frequencies. And that's it. That's all I have to present today. And I think we finished with 5 minutes left. So if there are any questions that I can try and handle at the moment, let's